In this next module, we're going to look at solutions. And I realize we've already done so much that required you to have knowledge of solutions, but there's even more that we can look at. So now that we have set ourselves up energetically and with equilibrium and knowing how to deal with some solutions, we're ready to deal with other units of concentration and also to look at how the properties of the solvent change when you dissolve something in it. So when we say solution, officially we mean a homogeneous mixture of two or more substances. The solvent and the solute are the components, right? One thing is the solvent, which is the majority component, and the solute is the minority component or minority components if you had more than one thing dissolved. Now, this feels like maybe a cheap designation, but we're going as generic as possible. You could mix two liquids together and call one the solute and the other the solvent. So this is why we're using majority and minority component definitions. And so, right, 51% or more means majority component. When the solvent is water, we'll call it an aqueous solution. Solutions undergo spontaneous mixing. If the solute is soluble, it will mix with the solvent automatically to become a homogeneous mixture. It'll go faster if we stir it, but if the solute is soluble, it will spontaneously go. It is thermodynamically favored for it to go, and we will have to deal with entropy, but it will just dissolve and mix together. For the solubility rules are just the beginning. We have done the not so soluble side of things in equilibrium. Now we will deal with the other side, which is it's soluble, how much can we put in there? And this is temperature dependent. So sodium chloride at 25 degrees, you can dissolve 36 grams of sodium chloride for every 100 grams of water. Beyond, like, this is the point that would get you to a saturated solution. So just as an example of what a solubility amount looks like. The mixing that happens in solution, I promised we would deal with entropy. It occurs to increase entropy, right? It's our measure of disorder. If you put something into a solution, break all the ions up and mix it around, you're definitely getting messier. This will also depend on if it's miscible. So this is the term for if the solute is a liquid, will it mix with the solvent? So that depends on the intermolecular forces. So intermolecular forces are the basis for our like dissolves like rule. So nonpolar solutes dissolve in nonpolar solvents. Polar solutes or ionic solutes will dissolve in polar solvents. Okay. The units that we will use to describe solution concentration, molarity is probably still the most common. We will still use molarity a lot. Moles of solution, moles of solute over liters of solution, nothing new about molarity. We will add molality, and the symbol for molality is this lowercase fancy m is what I usually call it. It's like, I don't know, italicized and in script letters instead of in regular print. Molality will come up in this unit. We will use it in some equations for what we're going to solve. This is moles of solute per kilogram of solvent. So it's just the solvent in the bottom, not the solution, and it's kilograms. It's not a volume, it's a mass. Molality, I think, is the most underrated unit. I'm an unreasonable fan of the unit of molality. Um, for molality, you can get a molality for a solution at any temperature, and the molality will stay the same. So the volume of a solution can change with temperature because density changes with temperature, and that can affect the molarity of the solution. I mean, probably not enough to make a significant difference, but depending on how sensitive your experiment is, it might matter. So molality will come up. I love molality, but it's awkward to say and we don't use it that often. Mole fraction is another way to talk about concentration, and this is the moles of solute over the total moles. So mole fractions have come up when we talked about gas laws. You can use mole fractions for solution, and it's still moles of solute over total moles. Mole percent is what you get when you take the mole fraction and multiply by 100. Right? The mole fraction is just the decimal form of the percent. And there are three ways that we do concentration that uses mass. Now, mass percent we've used in Gen Chem before. I mean, we used it in first semester, right? That is the mass of the solute over the mass of the solution, which like we did it with compounds or with like, here's a pile of soil or something like that. But it's still the mass of the part divided by the mass of the whole. And then if you multiply by 100, you get a percent. If you take that mass ratio decimal and multiply by 10 to the sixth, you get parts per million. So things that have a very low concentration, it would be worth multiplying by 10 to the sixth to give you something that's in reasonable units to talk about, so that you could say 20 parts per million or something like that. If the concentration is even lower, you might want to talk in parts per billion. So the mass of the solute over the mass of the solution, if you then multiply by 10 to the ninth, that would be a part per billion.